Okay, voltaic cells. So voltaic cells generate electricity. What is electricity? Electrical current is a flow of electric charge. And so here this is going to be electrons. And the electrons are going to be moving either through a wire or being carried by ions through a solution. And redox, oxidation reduction reactions can generate electrical current. If we look at zinc metal and copper 2 ions, zinc has a greater tendency to lose electrons, and so the zinc atom will transfer 2 electrons to the copper ion. The zinc becomes dissolved zinc ion, and the dissolved copper gets deposited on whatever the electrode is. Here it would be zinc as solid copper. And here is an illustration and a picture of this happening. So here we have a strip of metal, zinc, in a solution of copper 2 sulfate. The blue color is from the copper sulfate. And what we see happening is that electrons will be coming from the zinc metal, and they'll be given to the copper ions that are in solution. So that causes the zinc atoms to become ions, which then are soluble and float away. The copper atoms are not soluble, and so where they got the electron, they're just going to kind of sit there and stick there. And so what we see here is there's a noticeable decrease in the blue color because we've taken a lot of the copper 2 ions out of the solution. And then we see this black crusty-like stuff that's forming on this zinc strip. Now that does not look like copper, but it is just copper being deposited in kind of a messy way. Any questions? So if we separate the zinc atoms and the copper ions, we can force that electron transfer to go through a wire first, and that generates electrical current. So an electrochemical cell is a device in which a chemical reaction either produces or is carried out by an electrical current. So there's two types. There's the voltaic, which is also called a galvanic cell. And here we get electric current being produced from spontaneous chemical reaction. In an electrolytic cell, electricity is being consumed to drive a non-spontaneous chemical reaction. I'm not super big on whether you can correctly associate these terms with the correct kind of cell, because it's just kind of confusing, and honestly, I don't think it's all that critical. So how would you do that? Well, here's an example. This is a really low-tech way of doing it, very old school. So here we have a beaker that has copper nitrate in it and a copper electrode, solid piece of copper metal. Over here we have a solution of zinc nitrate and a zinc electrode. Then we can connect a wire to these electrodes, run it through either a voltmeter or something like a light bulb, which will let us know when current is flowing, connect it to the other the other electrode. So as the zinc atoms are losing electrons, they're going to form zinc ions, which are just going to float around in the solution. And the electrons are going to go through this wire, through the light bulb, over here. And here at the cathode, those 2 electrons are going to be given to a copper ion, which will be reduced and get deposited on the electrode. So each half cell is going to reach equilibrium, but zinc has a greater tendency to ionize, so its equilibrium lies further to the right, and that causes the zinc electrode to be negative relative to the copper electrode. Of course, we can't just have current flowing in one direction, we need to allow it to return. And so this is a salt bridge. And so electrons need to return, and so the negatively charged ions can move through this salt bridge over here so we can equalize the charge. Any questions yet? So electrical current is a little hard to think about because it's very abstract. I mean, it's fine to talk about electrons moving through a wire, but, what on earth is that? It's a lot like flowing water. So the rate of electrons flowing is like the rate of water moving. So we could think of the Kings River. I don't know if you guys ever pay any attention to that, but there's a dam, Pine Flat Dam, that controls the flow of the river. And you can actually go online and look at the current flow. And if, sometimes it's up around 15,000 whatevers, and other times it's down around 7,000. And so there's a variation in flow, right? How much water is cubic feet per second, I think. How much water is going past a point in a given period of time. So the rate of electrons flowing is just like the rate of the river. The unit is called an ampere, often abbreviated amp, and the symbol is capital A. That's the unit of electrical current. So that's how fast the electrons are moving. And then that is defined as 1 coulomb per second. So for the water, we talk about a cubic foot of water per second. We can't talk about cubic feet of electrons because that just would not work. So we talk about a coulomb of electrons per second. So what's a coulomb? A coulomb is 6,242 times 10 to the 18th electrons. Right, well, that's kind of a random number. Yeah, they chose that for other reasons, and we're not going to get into that. And you don't need to memorize that number. But just know that a coulomb is a big number of electrons. So why does water flow from Pine Flat Dam down the river? Because it's going downhill, right? Pine Flat Dam is at a higher elevation than, say, Reedley or Kingsburg. And so water flows downhill, just like balls roll down hills, right? Because of potential energy. So the water current is driven by a difference in gravitational potential energy, and similarly, electric current is driven by a potential difference. It's just not gravity. It's a potential difference, which is the measure of the difference in potential energy, joules, per unit of charge, coulombs. So a volt, capital V, is a unit of potential difference. 1 volt is 1 joule per coulomb. So we do have to, become a little bit familiar with some of these units that are really more physics units. So if we have a large potential difference, we get a large difference in charge and a strong tendency for electrons to flow. And this is going to be like a steeply descending stream bed. So if you say, look at where the water is being released from Pine Flat Dam, it comes out at the top of the dam, and then it falls, I don't know how many feet, but a significant number of feet before it hits the river, right? And so there's a very steep drop. Whereas when there's a gradual drop, when there's just a very slight change in elevation, then the water is going to flow more slowly. Does that make sense? So if we have, it's really high here and it's really low here, this water's going to be going fast. If it's almost level, it's not going to be moving much at all. If it's completely level, then we call it a lake, and it's not moving, right? Why isn't it moving? Well, there's nothing energy-wise to make it move, right? It's going this decreasing potential energy. So another word for this potential difference, the force that results in the motion of electrons, is electromotive force, or EMF. Any questions? So the cell potential, E cell, or the cell EMF, two different ways of talking about the same thing. It's the potential difference between the two electrodes in that cell, the voltaic cell. It's like the difference in elevation from the beginning of the stream to the end of the stream. So that cell potential is going to depend on the relative tendencies of the reactants to undergo oxidation and reduction. If we have something with a high tendency towards oxidation paired with something that has a high tendency towards reduction, then we get a high positive cell potential, and electrons are going to flow more rapidly. So that's one of the things it depends on. It also depends on relative concentrations and on the temperature. So we refer to a standard cell potential, E with the degree symbol there, that means it's standard cell potential. And this is going to be at concentrations of 1 molar for solutions or pressures of 1 atmosphere for gases. Those sound a bit like standard conditions that we've used before? Yeah, they're the same standard conditions. Okay, quiz time. Which statement best captures the difference between volt and amps? A volt is a unit that quantifies the difference in potential energy. The amp is the unit that quantifies the flow of electrical current. Or the amp is a unit that quantifies the difference in potential energy, and the volt is the unit that quantifies the flow of electrical current. Or third choice, there are 2 different units that measure the same thing. They measure the flow of electrical current. It's A, yeah. These can be hard to keep straight. They can. So in that voltaic cell we were talking about with the zinc and the copper ions, the standard cell potential for this is plus 1.10 volts. If instead of zinc we use nickel in here, that standard cell potential is going to drop to plus 0.62 volts. And the reason that it drops is because nickel has a lower tendency to be oxidized than zinc does. We can also end up with a negative cell potential. And what that means is that the forward reaction is not spontaneous. The reverse reaction would be spontaneous. Okay, so here's some things that we do need to remember, figure out a way to remember them. Oxidation occurs at the anode. Reduction occurs at the cathode. Again, pairs of things that you have to associate correctly. This is what helps me. Oxidation and anode both start with vowels. And red cat, reduction, cathode. So red cat. The anode is going to be more negatively charged. And the way I remember that is that anions are negative. So that means that the cathode is more positively charged, and cations are positive, right? So anode and cathode, the anode is more negative, the cathode is more positive. Oxidation occurs at the anode, reduction occurs at the cathode. So what happens is that electrons are going to flow from the anode that has a negative charge to the cathode. This makes sense because like charges repel. You have electrons negatively charged at a negative electrode, and they want to get away, and they're going to be attracted to the positive electrode. Any questions? So, like I kind of mentioned before, if we have electrons flowing from the anode to the cathode only, then we would cause a buildup of charge in the solutions, and nature doesn't like that very much. So in this voltaic cell, we need to provide a way for the charge to get back to where it started from. And so in these more primitive cells, we'll often use something called a salt bridge. And this allows counter ions to flow between the half cells while not allowing the solutions to mix. And so one way to create this is an inverted U-shaped tube that has a strong electrolyte in it, and that's going to be connecting the half cells. It's called a salt bridge. So the negative ions in the salt bridge are going to move to neutralize the accumulation of positive charge at the anode. The anode was originally negatively charged. If a bunch of electrons have left, now it's not going to be negatively charged anymore, and things are going to stop. So as the electrons leave the anode, then the negative ions will be attracted to that absence of negative charge, positive charge. And the positive ions are going to flow to neutralize negative charge at the cathode. So here's that picture again. So this is a glass tube, and it's got some plugs here that allow ions to pass, but doesn't allow solution to pass. So we can't get mixing of these two solutions. Because if we allow these to mix together, then the electrons will just go directly from the zinc to the copper ions, and they won't go through the wire, and we won't get it to do any work for us. So electrons leave here and travel over here, and that leaves sort of a void here of negative charge, and so the negative ions in the salt bridge are going to move this direction. As negative charge builds up over here, it's going to attract the positive ions in the salt bridge so that we can keep things charge neutral. Any questions? We have an experiment coming up where we're not going to make anything this big, but we're going to make a smaller version of this. Instead of a salt bridge, we're going to use a piece of string that's soaked in potassium nitrate, and we'll have two little wells that we put some solutions in, and we can stick some electrodes in there and put the string across, and then we can measure the electricity flowing from one solution to the other. This makes me think there's something else. No, I wonder why it's all on the left side. I don't know. So in a voltaic cell, in which direction do electrons flow? From high potential energy to low potential energy, from the cathode to the anode, or from low potential energy to higher potential energy? Yeah, it's going to be A. So just choosing between A and B, we can kind of just use some common sense, right? Things go from high potential energy to low potential energy. So this is sounding good. This sounds like opposite, right? So that one's not good. But then we also have to look at this one. Well, from the cathode to the anode, which is positively charged, the cathode or the anode? The cathode is positive because cations are positive. The anode is negative because anions are negative. Do electrons go from positive to negative? No, they don't. Oh, I thought there was something here. So this is another way that we can look at it. So if we have two beakers here, and they have a connection between them, and we have a low height of liquid in one and a high height of liquid in the other, which direction is the liquid going to flow? Well, it's going to flow from the high potential energy to the low potential energy, right? They're going to go until the level is equal in both of them. So line notation, also known as a cell diagram, can be used to represent an electrochemical cell. So this is line notation for the cell we've been talking about. So this double line here represents the salt bridge. We put the oxidation reaction on the left and the reduction on the right, just because. And so on the left, we have a zinc electrode, so solid zinc, and zinc ions. These are in different physical states, so we separate them with a line. Over on the right side, we have copper ions and copper solid. And those are in different phases, different states, so we separate them with a line. If you have two things that are in the same phase, they're just going to get separated by a comma. You can have all the principal species in a half reaction being aqueous. So here the copper is participating in this. What if it was going from copper 2+ to copper 1+? Well, they're both aqueous. Then you need something in there to attach your electrode, your clip to, right? So then we would use some other type of metal, something inert like platinum. It's not going to react. Okay, so let's look at this redox reaction and figure out what the oxidation and reduction reactions are and see how that relates to the line notation down here. So oxidation is loss of electrons. Reduction is gain. Wait, that's not what I meant to write. Reduction is gain of electrons. So let's see if we can figure out what's gaining or losing electrons. Here we have iron with no charge, and over here we have iron with a +2 charge. Is this iron losing electrons or gaining electrons? It's losing them. So then this is going to be the oxidation reaction because this is being oxidized, it's losing electrons. So I've got the 5 Fe solid, oops. And then over on the right side, I'm going to have 5 Fe 2+. Do I need any of these other guys in here to balance this? No, I just need some electrons, right? So this is losing electrons. The electrons are going to be the product. Each iron is losing how many electrons? 2, and there's 5. So this is 10 electrons. So then the reduction reaction must be the other one, 2 MnO4 minus. And now those other things, the hydrogens and the waters, have to be in one of these, so they must belong to this one. 16H+. This is the reduction half reaction, so this is gaining electrons. So I'm going to leave a space to put the electrons. And then we're going to end up with 2 Mn2+ and H820. If we just look at manganese here and manganese there, we're like, I don't know how many electrons we need. We'd have to look at the oxidation state, which we could do, but I don't feel like it right now. We can also fill this in just by looking at the charges. So here I have 2 negatives, right? So that's -2, and this one's +16. And over here I have +4. So together what I have here is +14. So how many electrons do I need to bring this down to 4? 10. It's the same as the number of electrons on the other side. So last week we learned about balancing half reactions. So what we did here is sort of the opposite. We took a balanced redox reaction and we pulled it apart into its half reactions. So when we draw the line notation, it matters which one is on the left and which one is on the right. And that can be hard to remember. Let's go back and look at this illustration. We have the anode on the left and the cathode on the right. And that's how they always draw them. So the way I remember this is that A comes before C. So anode goes on the left side and cathode goes on the right side. So this side is the anode, and this side is the cathode. And this is where the reduction is happening, right? Red cat. And this is where the oxidation is happening. So this is the oxidation. We've got solid iron and iron 2+, and so those are the two things participating in this oxidation. Here we have our salt bridge, and then on the right side we have the reduction, and so we have MnO4 and hydrogen ions, and those are both aqueous, so they're separated by a comma. And then the product is manganese 2 ion, also aqueous. I left off almost all of those things. So again, that's separated by a comma, and the line here represents the difference between aqueous and solid. In these guys, there's nothing you can attach a wire to. So we need something in that solution to act as an electrode, and so that will be the platinum. Any questions? So this is an illustration of that cell. On the anode side, we have an iron electrode and iron ions in solution. On the right side, we have an inert platinum electrode, and in solution here, we're going to have manganese ions, permanganate ions, and hydrogen ions. The water doesn't get shown here because it's an aqueous solution. We've got a salt bridge here, and the electrons are going to flow from the anode to the cathode.